In this video, I'm just going to specifically focus on part E of this question. This one says a boat travels across a river in which the water is moving at a speed of 1.8 meters per second. They've shown that there. The velocity vectors for the boat and the river water are shown to scale in figure 1.1. In still water, the speed of the boat is 3 meters per second. The boat is directed at an angle of 60 degrees to the river bank. So it's kind of like the boat captain says, well, let's go off this way because the water is going to push us this way and maybe trying to just go straight across, right? So this is vector addition. We've got the velocity vector of the boat, and we're going to add the water to it and kind of see what the resultant is. It says draw a vector triangle or a scale diagram to show the resultant velocity of the boat. So you can solve vector problems with scale drawings, and they tell us that this is to scale. In other words, they've actually drawn this line to scale with this line such that this length represents 3 meters per second, and this length, a bit shorter, represents 1.8. Okay, so it is to scale. Like you could, if this was like a printed hard copy in front of you, you could get a ruler and you could measure this, and you could choose a nice scale and you could say, okay, that many centimeters equals this many meters per second. It might be easier to set your scale on this line, or like this many centimeters represents this many meters per second. And you could translate this vector in space. The important thing about this vector is that it's this long. That's the how much, right? Remember, vectors tell us how much and which way. So that's the how much, and the which way is that way, right? Like it's pointing in that direction. So the rule for vector addition is that we place vectors head to tail and connect the tail of the first to the head of the last. Right now, they're just sort of vectors in space. So let's translate this vector over here. And they're showing the direction here. They put the arrow sort of in the middle of the vector, but we know that that's the head of it over there. So like this vector points that way, this vector points that way. And again, if you took the time to sort of use the scale drawing, you could actually use that scale and measure this line and use your scale to solve it. So scale drawings work. We're going to solve it with a little bit of mathematics stuff. I want to show you how to resolve a vector. A vector that points like this, up and to the right, has components that are to the right and components that are up. So it's taking a vector like this, that's like a hypotenuse, and forcing it into a right triangle, breaking it down into its x and y components. And we call that resolving the vector. So to answer this question, draw a vector triangle. The vector triangle I will show in pink. There's your boat velocity vector. There's your water velocity vector. And here's your resultant, right? Connecting the head, the tail of the first to the head of the last. And so that's the vector triangle that is the solution to this number. I'm drawing a different triangle over here because I want to solve part 2, determine the magnitude of the result. In other words, how much is this? I want to solve it with mathematics calculations, not with a scale drawing. It suggests that you could solve it that way. You know, it says, or a scale diagram to show. Determine the magnitude. So how can we solve this with a little bit of number crunching? I'm going to take my velocity vector, the boat velocity vector, and resolve it into its x and y components. The nice thing about the water velocity is that it's just an x component, like it just goes directly to the left. And so it's easy to add vectors that are like tug of war situations. Imagine that one team pulls the tug of war with 10 newtons of force this way. The other team pulls the rope with 5 newtons of force that way. What's the sum of those two vectors? 5 newtons that way, right? Like if they're opposing each other, you just subtract them and say, oh, 10 newtons this way minus the 5 that way. So I have a net force of 5 newtons that way. So this left vector opposes the right component of the boat's velocity. The boat's going sort of against the flow of the water as it travels this way so that it kind of rights itself, right? And it's going sort of straight across the river like this. So if here's a 3 meter per second velocity vector, right? Like this is the boat's velocity represented by this hypotenuse right here. So that velocity is 3 meters per second, labeled right there. And there's a 60-degree angle right here. I kind of want to know, well, what is the horizontal component of that velocity? What is the vertical component of that velocity? So I can use sort of subscripts like this, or I could call this X and Y if you like this is X-axis, that's the Y. I'll stick with horizontal and vertical. Since I know this angle is 60 and this angle is 90, I know that's the hypotenuse. I should be able to use some trig functions to solve this. The horizontal component of the boat's velocity is adjacent to the 60-degree angle, which means the cosine function is helpful here because the cosine of some angle is equal to the ratio, the adjacent side, the horizontal component of velocity, over the hypotenuse, and I know its value is 3. So that's a perfectly solvable math problem. I can calculate how much of this boat's velocity is going to the right by multiplying both sides of this by 3 meters per second. So everybody with a calculator knows that the cosine of 60 degrees times 3 is oh, no, wait, no, it's not. I think I solved for the vertical. No, that's right. Yeah, because cosine of 60 is a half. That is good. Yeah, cosine of 60 is a half. Half of 3 is 1.5. And so of this 3 meters per second, because it's going at a 60-degree angle, 1.5 meters per second this way. The vertical component could be solved using the sine function, right? Because it's opposite this angle. So I could remind myself that the sine of some angle theta, in this case 60 degrees, is equal to the side opposite that angle, in this case, the vertical component of my boat velocity, over the hypotenuse, 3. And again, taking the sine of 60 degrees, multiplying both sides by 3 meters per second, I can solve that the vertical component of velocity is just sine 60 times 3, which equals that's what I was about to say. 2.6. I already had a calculator. I was just giving everybody else a chance. Yeah. 2.6 meters per second. All right, now what's this resultant? Okay, what is the magnitude of the resultant velocity? So this vector right here has a component that's going a little bit to the left and a component that's going up, right? So like the up component, the vertical component, just comes from the boat's velocity. What I need to do is add my lefts and my rights. So the horizontal component of the boat's velocity is 1.5 to the right, but the water velocity is 1.8 to the left. So what is the net horizontal velocity of this vector right here? So the boat's going that way because it's got an up component equal to 2.6. That comes from the boat's vertical component velocity. It's got a left component equal to what? How many people out there are thinking 0.3, but just a little bit too afraid to offer that? Good. Yeah, 0.3. Because 1.5 this way, 1.8 that way, the tug of war, who wins? The water velocity wins, but only by a little bit, right? There's a net velocity from the water of 0.3 going to the left. What we do is maybe I'm going to redraw this result over here to just sort of make it a bit, clearer. So this vector right here is a vector that's resulting because there's 0.3 meters per second that way and 2.6 meters per second that way. And so those are legs of a right triangle. I can solve for the resultant using Pythagoras' theorem. Now that I look up at the projector, that's less clear. Sorry about that. It's very clear on my computer screen. Maybe it is for you too, following along at home on YouTube. Leave a comment down below if it's tough to see. All right, so this is our 0.3 this way and our 2.6 that way, or up, okay? That's the legs of this resultant right here. Again, we sum the horizontal components because they directly oppose each other. So we can just add them up like this. Add up the x's, add up the y's, draw a new triangle. There's the sum of my x's. The sum of my y's was easy because all I had was a y component from this, right? This didn't contribute to the y component of the resultant at all. It just affected the x component. So computationally, I should be able to get the magnitude of the resultant velocity by taking 0.3 squared plus 2.6 squared and taking the square root of that, right? And that's just using Pythagoras' theorem, saying this resultant squared is equal to a squared plus b squared equals r squared plus c squared, whatever you want to call it. So I still have that value 2.59807, whatever, in my calculator. So rather than like rounding it to 2.6, I'm just going to square that. And it's 6.75 plus 0.3 squared equals 6.84. And so the magnitude of the velocity squared is 6.84. So I take the square root and I get an answer of 2.62. In other words, this hardly contributes at all, right? It's like if this is 2.6 and that's only 0.3, then this, right, like this is actually 2.59 something. This is actually 2.62, like 2.615. If we look at the slides, great. If you look at the slides on focus, we'll see sort of an example like this. How do you add two vectors A and B when they're not perfectly lined up with the x and y axes? Like this isn't too bad. If something's at right angles, we know we can use Pythagoras' theorem to solve it. If they just oppose each other like north and south, we just subtract them. If they're in the same direction, we just add them. The toughest thing is when we got vectors like this. The way to go about solving problems like this, like you could use something like the law of sines or something like that, if you know the law of sines and you're given enough information about that. But what I'd like you to get in the habit of doing is realizing that vector A here has an angle theta A, let's call it. And vector B here is at some angle theta B relative to the horizontal. And so any vector that goes up and to the right must have a component to the right and must have a component up. You could call it like A sub x, A sub y. This vector B has components, B sub x, B sub y. And it will be true that if I resolve vector A and if I resolve vector B using the trig that I just kind of showed you, using the sine and cosine to sort of break down what this hypotenuse is in terms of x's and y's, then this resultant R is going to have legs that are equal to AY plus BY, right? There's my AY vector here. There's my BY vector here. In other words, vector A brought me up this much. Vector B brought me up this much. And so the resultant brings me up the sum of those two. Likewise, A brings me over that much. B brings me over the rest of the way, so that my resultant X is just equal to the sum of those two components. My resultant R, right, is equal to the sum of AY and BY. So the toughest type of problem like this might be where you're given two vectors that are kind of at angles that aren't, straight up and down or left and right. You got to do some trig to resolve them. You got to add up the y's to get the net y. You got to add up the x's to get the net x. You got to draw a new triangle, y, rx, and then there's my resultant, right? And because I know these values, I can just use Pythagoras' theorem to solve it. And that's kind of what we did. just a minute ago, except for one of our vectors we added didn't have a y component, right? So we only had to resolve one of them, and then we just said, oh, the water brought us back this way, And in fact, it brought us back more than the component this way, because it was only 1.5 this way, is 1.8. So in general, adding two vectors A and B can be solved by resolving the vectors into x and y components, adding up the x's to get the net x, adding up the y's to get the net y, and then recombining that and using Pythagoras' theorem, to solve for it like this. Okay, and then just solving for r using, a squared plus b squared equals c squared. That's the same thing as that. It just looks a bit different. Hopefully this explanation was helpful. If not, leave a comment down below. Ask any clarifying questions you might need. More practice will kind of make perfect on this. Let's see some other examples. Check the link below.